the admin for the UCSB Physics Discord. I will be the one conducting the interview with the legendary Dr. Omer Blaes. You do have a bit of clout on the server, and we have a couple of emotes based on you, so you've gotten a little bit of popularity, and so we decided it was most appropriate to have you as our first interview guest.
I'm honored. Wow. And
No,
very, very flattered.
the
Yeah.
honor is mine that you would give us an hour of your time, and so I hope to make the best use of this time possible. And I guess for a little background, could you introduce yourself and like give us your like academic history on like how you got to UCSB from like an undergraduate, just to give us a sense of like what a professor's journey is like, starting from where we are right now.
Sure. I'm going to start a little bit earlier because in order to explain the why my trajectory went the way it did. So I was born in the US. I'm an American citizen, but my father was in the military, and we were stationed in the UK when I was age 12. Then my parents got divorced, and a complicated family history, but I ended up growing up in the UK from the age of 12 onward.
Okay.
And so I did my undergraduate at the University of London at Queen Mary College. And then I did my PhD in Trieste in Italy,
Wow.
at the International School for Advanced Studies. That was because at the time I didn't know what I was doing. And there was a person I was interested in working in Oxford, but he was moving to this new school in Trieste. And so I decided to just go and live in Italy for a few years.
Oh.
And then when I got my PhD, I lucked out because I did some research that some people at Caltech recognized. And so I was hired as a postdoc at Caltech. And then I did another postdoc at the University of Toronto in Canada. And then I landed a faculty position at UCSB, and I've been there ever since. Yeah.
Well, I'm surprised they use the term lucked out. Someone as, I went over your CV a little bit before we came here, and you have a lot of papers published. Someone as accomplished as you would still use the term lucked out in your career? Really?
Oh, yeah.
Really?
Yeah, no. Anyone who tells you that they got to where they are because they worked hard, I mean, we all work hard, or because they're brilliant and inherently brilliant, no, that is not true. There is a lot of luck involved, including luck in being successful at research. Sometimes you just manage to hit on an idea that works out to be great. So no, there's a lot of luck involved, a lot.
Oh. Wow. Okay. So
I don't know whether that's good news or bad news for you.
I think it's rather bad news for undergraduates who realize that they could do everything right in terms of like asking professors and knocking on doors and getting good grades, and just not getting a position in graduate school if they want to go to graduate school, just because the luck wasn't on their side. Like, I got very lucky in being able to snag a summer research position, and I attribute it to luck that I was in the right place at the right time to get on board with the project. And so I just can't think of someone. I can think of people who just maybe not have the fortune of having this project appear in the right time. Like, they're too young, they're freshmen. And so I just can't think, there's a lot of luck involved. And so it may be disheartening to you all guys. It may be disheartening, but like, that's just a fact in life. And it was just something that we have to all deal with. Professor Blaes dealt with it. I got lucky, but sometimes I got unlucky too. There's ups and downs.
Yeah, and I would add, part of luck is part of having good fortune or having good luck is being willing to seize opportunities, to go for them, to try, and throw your hat in the ring. And so everyone has opportunities come their way, or most people have opportunities come their way. I can't claim everyone. And yeah, you have to be willing to seize them. And this is true no matter what you end up doing with your life. This is true in your personal life. It's true in your career. It's just being open to opportunities that come your way, and seizing them when you know when they're right for you.
Okay. So I would I would like to move on to I guess the biggest topic that undergraduates always ask professors, which is research. Like, how do I get research? What is research like? I think I'd rather than give you such a vague topic, I'd like to start with something more specific. Excuse me, let me pull up something here. Oh, Twitch is full screened. That is why. I guess we'll start with a little bit of a tangent before we dive into your research on astrophysics, black holes, compact objects, and high energy physics, which I find all interesting, and a lot of us find it interesting. But just a little bit on the side, what topics do you find interesting outside your main field of specialty?
Oh, okay. There are lots and lots of things that I find interesting. Uh, let's keep it within physics, though, okay?
Yeah,
Because
let's keep it
there are
physics.
lots of things that I find intellectually interesting in a whole bunch of fields of human endeavor. But within physics, I think the things that I like to hear about most are issues in biophysics, particularly developmental biology, and how what's it called, morphogenesis. That strikes me as absolutely fascinating. I love, even though I don't understand it, I love hearing about the black hole information paradox and how, apparently quantum information has solved that problem or is a very darn good possible solution to that problem. Um, uh, um,
I remember you told us about a little bit about music when we were in 104.
was I going to tell you about music
I
or?
think you did when we were doing like harmonics, or not harmonics, when we were doing like um something, and then we were doing something, and then music came up, and it was a year ago, so I can't put my
It could have
notes.
been. It could have been harmonics as being abstract vectors in basis vectors in an abstract vector space. That could have been one thing that I could have linked that to the mathematics of normal modes.
Okay.
Yeah, that could have been something. And yeah, music would be another thing. In fact, there's a student, Sarah, who's one of my learning assistants, who has promised to teach me a whole lot more about the physics of music. And I'm really looking forward to talking with her about that. That is something that I would like to learn a lot more about. Just what is the physics behind what makes music so great and so pleasant to the ear? It's something I know very little about.
So, Professor, what made you decide to pursue an academic career in physics? Like, what?
So it was largely because ever since I was a kid, I was fascinated by astronomy, almost with a sort of childlike wonder, not really knowing what it really was in terms of research. And then as I, progressed through school and high school and college, I found out that I was pretty good at math and physics, and so this thing just sort of gelled, and I wanted to do astrophysics. It was just, and it really was a sort of almost silly, immature fascination with the field, but it just resonated, and it continued to resonate and resonate and resonate. And as I got older, I just pursued it doggedly because this was something that always fascinated me. So that's how I got into it, believe it or not.
Uh, what was your undergraduate life like? Like, can you compare it to like what undergraduates have to deal with now and today?
Oh gosh, no, because I didn't live through a pandemic.
I
I
guess we'll say first of all, let's outside the pandemic first, and then we can factor in the pandemic. Like in normal times, well, if you can you compare the undergraduate life that you experience with the ones that you see us experiencing?
it's still somewhat different. I mean, yeah, I mean, I will put the pandemic aside, but let me just say the pandemic has completely altered what the university experience is for all of you in a very, very negative way. And I just thank you for, setting up this Discord to create some sort of social space for all of you. But yeah, I just can't imagine. I really just feel for all of you. At any rate, my undergraduate experience was not disrupted by a pandemic. I was in a big city in London, in England. I had never lived in a big city before in my life, and so part of the enjoyable thing was being able to take advantage of all the culture that a big city has. Uh, so so in my social life, I made friends, and we would go out all the time. Not all the time. We would go out a fair amount. Punk rock was the thing of the day, and when I was that age. Although my favorite band was Queen at the time, so I saw them in concert many times with Freddie Mercury and everything.
Oh my god,
Uh,
I wish I could have
uh,
seen a Freddie Mercury concert in live.
yeah, no, that was my era. I mean, I hate to, yeah, that's how old I am. That was,
It was a good. That's a good era though. Was the food
uh,
better? Was the
I'm
food
sorry.
was the food better in your undergraduate?
Oh no, the food was awful.
It was awful.
And I didn't have a lot of money, and so we lived hand to mouth. Uh, so yeah, I mean, I get that aspect of being a student. I mean, we lived away from the campus, which is in the East End of London, in an apartment sort of in the northeast of London, and so I was away from the university, but in this big city, so I could really enjoy it. Academically, the British system is a very different system. So from the age of 16 onwards, I was only studying math and physics, no English, no history,
Wow.
no arts, no humanities, no social sciences, no nothing, just math and physics, math and physics. Um, and so it was a very narrow, focused course of study. But I learned as much as I could. And then try to get my arts fix from living in London.
Do you feel like you learned more math and physics during your time as an undergraduate compared to what's being taught at UCSB during the undergraduate curriculum?
Yes, I think that's true. So because it's so focused, I think my level of physics knowledge was deeper than a typical undergraduate physics degree here at UCSB. Uh, However, my PhD, there was almost no coursework. It was just research from the get-go, and I will say that my knowledge of physics at that time was not as deep as a typical physics PhD student here in the U.S., where the graduate courses take you deeper. So I was sort of in between a typical undergraduate, an American undergraduate physics major and a PhD, just in terms of course knowledge. I mean, research is a whole other
Research is a whole
thing.
other topic.
Yeah.
Much
Much of what I've learned to get as deep as a typical American is through teaching
through
over my
teaching.
career. Yeah.
What about teaching do you enjoy the most?
Two things. It's learning physics more deeply, and that comes about just by, teaching a subject that I don't use much in my research career, and by teaching it, I learn it more deeply, uh, uh, and just by preparing the lectures, but also it's having students ask me their naive questions that always come out of left field and make me think, force me to get out of my rut of thinking and think in a different way. And then I realize something about physics which I never realized before. This happens to me over and over and over again.
Did you,
Um,
did you find teaching initially challenging? Like, did you like when you first started teaching, did you have thoughts of like, oh, I may not actually know enough about this subject to teach undergraduates because, like, for example, I did astrophysics, so like my quantum mechanics are shaky. Like,
yeah, that's absolutely right. And sometimes I over my career, I've actually purposely asked. So as an example, I taught graduate quantum mechanics the entire year sequence, and I did that because I knew my quantum mechanics was shaky, and I just wanted to learn it more deeply, and so I just volunteered to do that. And I've sort of done that throughout my career here. I just bounce around the curriculum because I sometimes I get bored with a particular subject, and I just want to learn another subject more deeply, and this is one of the joys of being able to teach physics. I should say there's one other thing that I
Uh-huh.
enjoy about teaching, and uh, I enjoy you all. I mean, I really, literally enjoy interacting with you all. I just love it. And that's another thing that I'm missing about. I mean, Zoom isn't quite the same thing.
No, it's not.
Yeah.
It's not. Um, we hope to continue these. Like, let's say, even though we get back in person, we hope to still continue the Discord and maybe offer these interviews, instead of over Zoom, but in person, and then have them streamed, like almost basically like a news, like basically like you would see on TV, just two
Mhm.
people talking, and then it's streamed onto Twitch, and then hopefully we give you a chance to connect with a lot more students in than usual, but that's me rambling about a future project of ours that I should not be revealing. So let's pretend I
Well,
didn't
but
say that.
kudos anyway.
Let's pretend I didn't say that. Um, I
You're being
guess,
recorded, right?
yeah, I mean, like now it's on the record that these are my plans. Now I actually have to put them to fruition. So we'll see what happens. What about your current research excites you the most?
Uh, right this instant, the research that I'm doing that I'm most excited about is with one of my graduate students. And well, no, there are multiple things. No, there are many things. But I'll just give you one of them. So we're doing simulations of material falling onto the surface of neutron stars, which are very, very dense, basically gigantic atomic nuclei. You squeeze the entire mass of something like the sun to the size of the city of Santa Barbara.
Uh-huh.
And all the electrons and most of the electrons and protons combine to make neutrons, and you make this just giant ball of neutrons. And these things, they're very dense. They're on the very edge of just collapsing onto a black hole. So their gravity wells are as deep as you can be without being a black hole. And when material falls onto them, the material gets very, very hot and glows in X-rays. And so you see accreting neutron stars, which are ripping material off of, say, companion stars in a binary system. And this material comes down and hits the neutron star and it glows. That's not why I'm interested in them. The reason why I'm interested in them is that the neutron stars have these ultra strong magnetic fields. These are the strongest magnetic fields that we know of anywhere in the universe. And those magnetic fields funnel the accreting material onto the magnetic poles of the star. And so often we observe these X-ray sources as X-ray pulsars because the magnetic axis is misaligned with the rotation axis of the star. And so you get these sort of hot spots that swing in and out of motion.
I'm sorry, I missed it. Were these magnetic I'm guessing this was like X-ray jets coming out from the neutron star or from the star by
It's material coming from the companion star, which then is guided by the neutron star's magnetic field onto the magnetic poles of
onto the
the
magnetic
star.
poles, and that's what creates radiation.
Yeah, it's somewhat analogous, although it's a much more collisional system to the aurora on the Earth,
Oh, okay.
where material is guided by the Earth's magnetic field onto the north and south magnetic poles and crashes into the atmosphere and causes fluorescence and optical light. Although it's in the neutron star case, it's what makes it physically interesting is that the material that the systems that we observe, the accretion rates are so high, the mass inflow rates are so large, that the material gets dominated by photon pressure rather than ordinary gas pressure. So there's so much radiation that's being generated that the photons themselves are actually pushing the material out. And it turns out that when we observe these systems, many of them have luminosities, observed luminosities, that exceed a critical value where the outward photon pressure would actually exceed that of gravity. And so then you ask yourself, well, how does matter get in if photon pressure is pushing out, with a greater force than gravity is pulling you in? And it's partly because the material is being guided by the magnetic field, and most of the luminosity actually comes out sideways rather
Okay,
than
so it's
along the guide field. But even then, it's been known for a couple of decades now that this sort of equilibrium of this magnetically confined plasma should be violently unstable. And my student has successfully simulated the nonlinear evolution of this instability, and we are now learning about what these accretion columns might really look like for the very first time, and how we might be able to make predictions to compare with observations.
uh,
So that is one thing that I'm really excited about.
is said student a graduate student or
He's a
undergraduate?
graduate student.
Graduate
Yeah,
student.
that's
Okay.
right.
How do you come up with projects like these? Is astrophysics research mainly about simulations? What techniques and programs do you use most frequently? And I guess what kind of skills should someone who's looking for work in your field have?
They should definitely know how to do basic coding in Python at the very least. But to really to do well now, it's evolved over the course of my career. So I grew up as a sort of analytic theorist. I did a lot of analytic work. I mean, analytic and quasi-analytic. You have to solving ordinary differential equations on a computer is now considered to be analytic work. It's not really computational, even though you have to use a computer to do it. But the systems that we're dealing with are so complex that the most interesting astrophysical problems these days are often those that require big supercomputer simulations to try and understand. And that's where a lot of progress is being made. So if you like computational work, and if you like nonlinear dynamics, there are a lot of interesting problems to pursue in astrophysics. They're not all computational problems. There are other types of problems that a theorist can work on that don't involve, big, heavy-duty supercomputer simulations. But the problems that I'm most interested in that involve fluid dynamics really require the use of big computers.
So theoretical astrophysics is not actually like when I think of theoretical physics, I think, oh, pen and paper, and that's my entire laboratory. But I guess I'm wrong. It's really just computer simulations.
No, it's not just that. I mean, it always all of physics requires ideas, and these ideas could be an idea about a new type of simulation. It could be a new approach to a problem. It could be just simple order of magnitude estimates, not even solving differential equations, but just making an estimate for how big an effect should be, and then trying to see whether that might explain a phenomenon. Every time a new phenomenon is discovered in nature, that's the first step, is what could this be? Let's do some twiddle arguments, some order of magnitude estimates to try and figure out what the most important effects might be, and what we could do to explain this phenomenon. And then as the field matures, typically the phenomenon gets, you're looking at more and more complexity within the phenomenon, and then yes, more and more computational power has to be brought to bear. So all of these skills are useful, actually. It requires a very deep understanding of a wide range of physics, because all of this stuff gets applied at the same time,
Mm.
typically, to explain the phenomenon. And then it requires a broad skill set in terms of theoretical techniques that you're using to solve the problem.
One of the questions I had prepared for you was, what is the single most important class or important thing that you think all new physicists should know? But from our conversation, I have a feeling that the answer to that is everything. If you want to be a theorist, like you really can't avoid learning everything if you want to do physics. Like you can't just avoid nonlinear dynamics because it sounds scary. That's me. Um, and then
But
expect to be a
right, but on the other hand, you can't know everything. I mean, all of us as physicists are limited by the fact that our brains have finite capacity. If only I had 10 human lifetimes, and if only I had a brain that was much, much bigger, that could store much more information, I would be a better physicist. But we can't do that. And so all of us, we learn the things that are necessary to solve the problems that we're interested in solving. And that goes again for everyone, whether you're an experimentalist, a theorist, an observer, whatever. You have to learn the skill set that you need to tackle the problems that you want to tackle.
I'd like to move on to some user questions right now. Let's see now. In the Discord channel, Jacob asks, quote, so does that mean when we were talking about how you switch courses that you teach, quote, does that mean that you'll teach classes other than 104 so that I can take more classes with you?
Thank you. Thank you for the implied compliment. Yeah, I'm slated to teach 104 next year, but after that, I think I'm going to be fed up with it and will want to be teaching something else. Yeah, I bounced through it. What is a course that I haven't yet taught that I'd like to teach 106, the nonlinear phenomena course.
Will that be next year?
No. Next year I'm teaching graduate classical mechanics in the fall, then undergrad classical mechanics in the winter, 104, and then I'm teaching our new Python course in the spring.
Is this a graduate Python course?
No, this is an undergraduate Python
New
course.
undergraduate Python course.
Yeah, a new lower division freshman sophomore Python course that will be required for all incoming physics majors starting in the fall.
Required for all incoming physics majors.
Yes.
It's not 129L. It is.
No, it's 29L.
Is it like kind of like a more basic level? Is it
yes, far more basic. It's just basically what is Python all about? I mean, crudely speaking, not deeply, and how can you use it to do an integral numerically, or to make a plot of some data? Just very, very simple tasks.
I think that would definitely be helpful because like I'm taking 129L and like thankfully I had prior programming experiences so that I was able to like kind of just Google everything and be like, oh, this is how you would do it. But like 29L, that sounds like a great class. And if it's for freshmen and sophomore, I feel like the freshmen and sophomore of this department definitely need a little more support because I feel like a lot of them fall through the gaps, especially during COVID. During COVID, it was one of our goals was to try to basically save the freshman class. And I don't know how good job we did.
Yeah. No, again, kudos for trying to do that. But I don't know whether you're all aware, but the department has been engaged in a massive reform of the entire Bachelor of Science curriculum. And it's with the Academic Senate right now. It's been approved by one of the committees, and it has to get approved by one more committee. But if it gets approved, the freshman, sophomore, and junior and senior requirements are changing over the next 2 years for future students. The current students can always choose to use the existing requirements. But yeah, as part of that, a Python course in the freshman and sophomore years is going to be required.
That's great.
Because we think we need, you all need to learn how to code, to do basic coding, and it'll be good for you and no matter what you decide to do with your degrees. And it will also enable us to take you a lot further in your physics courses, because you'll be able to use these computers to do a lot more things than just simple analytic calculations.
Next question from the crowd. This one is from a user on Discord called Mechanic. On the topic of teaching, what is your process for formulating something like homework and test problems? Do you have a regular source of, quote, inspiration?
Oh gosh. It's just, it's a combination of just ideas that come to me. Some of them are good ideas. Some of them are not so good ideas. Sometimes I give a very difficult final exam and just experience of the subject. Yeah, I do have a whole library of textbooks in all of these fields that I consult to try and get ideas. But often it's just sitting in the shower. I need to come up with a problem on this topic, and something comes to me. Um, so yeah, it's a scary process. So right now I'm scared about next week's 104 final because I haven't yet written it. As I was explaining to you, I was struggling with a LaTeX issue and in writing the exam right now. But yeah, I always panic before an exam. I know you all are panicking within the exam, but I always panic before an exam. Will I get it written? Will I actually come up with the problems that I need? And will the ideas come? And so far they're still coming, but yeah, I don't know how I do it. It happens
But you
somehow.
don't use any test bank resources or any like test
No,
analysis
no.
problems, or like you just from Blaes, fresh from Blaes problems. Okay. Oh, I think that answers that question. Let's see now. Um, what are your thoughts? Another question from Jacob in the Discord. What are your thoughts about undergraduates taking 205?
Oh, I think that's fine. If you've taken 104, 205 is within your power. It's just recognize that it's 205 is much more abstract than what you've seen in undergrad classical mechanics. It's full on Hamiltonian mechanics, and it's just a much more abstract formulation of mechanics. But it's the most powerful method, and it leads to incredible insights into how nonlinear systems evolve, how complicated mechanics problems work, what's going on deeply, and it leads to insights into quantum mechanics. And it's a beautiful course. I try and throw in some abstract differential geometry into it as well because it's a useful vehicle for learning some of that. But I also try and throw in real practical problems like even understanding the orbit of the moon around the Earth. And how it really works, and not just as a Kepler problem, as going around an ellipse, but how the orbit evolves, because a lot of this stuff was developed for celestial mechanics, and I'm an astrophysicist, and I know quite a few problems in there. So yeah, it's a great subject, but the problems are hard, the math is hard, and it's not something to be taken lightly. But if you're into that, yeah, I'm open to undergraduates taking it, certainly. Um,
Um, my question is, you sell this class, that's great, but if it's very difficult, then how are graduate students supposed to be able to do these classes while juggling their research obligations as well? Like,
it is not easy. And often graduate students in their first year don't make a lot of progress on their research. Some of them do, but the courses can be quite challenging. Yeah, so yeah, unlike my experience, as I was relating earlier, when I was a PhD student, I took almost no coursework. I mean, I did do some coursework, but the research was really what was soaking up most of my time. And that typically happens to American graduate students, including graduate students here at UCSB after their first year. But they should still be, sorry, I mean, most of you are not graduate students, or maybe all of you are not graduate students, but the graduate school is still about doing research, and even in the first year, they should be getting started with it. But yeah, it's hard. The courses can be quite challenging. Um,
could you elaborate more about the physics major restructuring that is starting next year? This is a question from Discord from Natalie.
yes. It's going to happen in two phases. The freshman and sophomore changes are going to happen next year. This is assuming it gets approved by the academic senate. So freshman and sophomore degree requirements will change next year, and then the entire four-year degree requirements will change the following year. So in the freshman and sophomore thing, there's the Physics 20 series is going to be reduced to 5 quarters from 6. So it'll only be 5 quarters long, and it will be in 2 staggered sequences, one starting in the fall, one starting in the winter. So students who are very well prepared can start it in the fall. Students who are less well prepared will be strongly encouraged to take a new course that we designed that basically teaches what the math department apparently doesn't teach well. Here's how you take a derivative. Here's how you take an integral. Here's how to take a cross product. Here's how
Oh,
to
I can't imagine physics students not being able to do that. Oh, no. Oh, no. I must have had a good high school education then.
Well, some students struggle with these things, and you know, trig. Here's how to use, and just basic math skills that you need as a physicist, and you learn them quickly, and so you're much better prepared to start in physics 21. There won't be a physics 20 anymore. Um, and then those staggered sequences, there will be multiple ways of getting, you know, of accelerating your path. Even if you start the new 20 series in the winter, you can still catch up in the summer and, you know, get as far ahead as you like. Um, there will be a new Python programming course that will be required. And we're also beefing up all the physics lower division labs.
Oh, wow.
So all three of them will be now full on 2-unit labs that will be a lot more interesting and useful for you all.
Interesting.
That's the lower division. And the upper division, the main new thing is that there will be multiple ways of getting a Bachelor of Science degree that involve taking concentrations in various subjects. There will be a sort of standard physics concentration. There will be an astrophysics concentration. There will be a soft and living matter concentration. And there will be an education, a physics education concentration, which we're doing in collaboration with the Gewurz Graduate School of Education. So
Why haven't this been implemented? See, this is where I lucked out, or this is where I did not get lucky. I could have used that. Man.
Yeah. So yeah. We're trying to make the bachelor degree much more flexible for students with various, you know, ideas as to what they want to use the degree for. And so with that structure in place, hopefully we can even introduce concentrations in other areas as we move forward. But those are the 4 that we're starting with.
Okay.
So yeah, that's the, oh, and we're, you know, switching some of the requirements around a little bit too, depending on the concentration.
Can I redo my undergraduate experience at get this new fancy degree? Is my since I'm graduating next year, is my current degree going to be worth less than the new fancy degree?
No, come on. It's still UCSB physics. Come on.
Okay. All right. I have a question from Kellen in the Discord. As the former department head, I heard that you were keenly interested in the physics transfer experience. What is the landscape like for transfer kids? Has it changed over the years, and has the department been changing to try to ease the transfer experience along with these changes you are talking about? How is it going to affect, basically, how are these changes to the degree going to affect transfers? Because
right. So we have thought about transfer students in these in talking about these curricular changes. The primary thing is that we're now going to, I don't think this is sufficient, unfortunately, but the main vehicle is 103, the first quarter of classical mechanics is now going to be a sort of ramp up course that sort of is to bridge the community college experience with the UCSB experience. And it's going to be, there's a lot more, well, not a lot more in it. It's the contents have sort of been changed in order to, again, focus on things that we think are going to be useful in dealing with the other upper division courses. There's going to be a bigger concentration on special relativity in 103. There's going to be a lot more about basic ordinary differential equations in it, and again, just to try and prepare transfer students to make it an easier transition from wherever the transfer student is from into UCSB. I think we need to think about a lot more than just that, even than just curricular changes, to better enable transfer students to transition successfully into the upper division courses. But that is part of the curricular reform.
Kellen complains that special relativity is useless. Which I actually share a little bit of sentiment about. Like, I do not know how much emphasizing more special relativity would have helped me with introduction quantum mechanics. Like, that was the big punch in the face from community college. Like, what is Hermitian? What is an eigenstate? Like,
okay, so another reform in the curriculum is that 102, what is now 102, is now going to be the required mathematical physics class.
Not what
that teaches you what a Hermitian operator is. That teaches you the abstract linear algebra that you need to understand Bras and Katz. That will be required before you take 115A.
That's a good change. Yeah, because it's like people often say that they recommend 102 before 115A, but I didn't know that before 115A.
Right.
So, like as a
Now
trans,
it would be an explicit requirement.
that's good. That's good. Let's see now. There's more going on in the chat. Um, no, they're just talking. Uh, when you decided to be a theorist, how did you practice the skills of being a theorist? Or what can you define as the skill set of a theorist, if there is such a skill set that you believe?
Oh gosh. Again, it's evolved since when I was a student. So um, uh, the more physics you know, the better off you will be. You really have to like doing computations, and whether they be analytic computations or numerical calculations on a computer, you have to just enjoy doing that. Uh, you have to be able to think, quick and dirty with order of magnitude estimates as well, particularly in my field in astrophysics. You have to, because again, the systems are so complex that there's no way you can get exact solutions for a lot of the problems that we deal with. Um, uh, you have to enjoy theoretical physics. I mean, and I don't know how else to say that. And this is not, and I'm not placing any value judgment on that, by the way. I could not be a successful experimentalist. And I think experimentalists have skills that go way beyond my skills. I look at them, just as gods or something. What an experimentalist can do, man, they are enormously powerful physicists. And they may not be able to do math as well as I can typically, but man, they have skills that I could only dream of having.
How much do you communicate with experimentalists in your work? Like,
A lot, a
how does
lot.
actual theory translate into experimentation? And like,
Yeah, well, I expect it's mostly actually what in astronomy are called observers. So the labor is sort of divided up into people who build instruments, people who use these instruments to make observations, although the people who build them also use them to make observations, and then the people who do theory. And there are people that straddle all three of these. Some people do all three. They do theory, experiment, instrument building, and observation. Those are a very rare breed, and some of them are more siloed. But yeah, the enterprise requires interaction between all three, and I interact a lot with observers in particular. Um, a lot of my research involves observations that have to be done from space, because the radiation that we're interested in just doesn't make it through the atmosphere to the surface of the Earth. And so I work with a lot of space-based observers who take existing satellites and collect data. And yeah, I have to work with them. Astrophysics is very, very closely tied between theory and data. Um, uh, and that's one of the things that makes it so great, is that the science really progresses rapidly, because there really is this play between theory and observation. And I have had theories completely destroyed by observations. I have had that experience.
does it feel awful, as I imagine it must be?
It's disappointing, to be wrong about to have an idea that turned out to be wrong, but it's also, you're witnessing the progress of our knowledge. It's good to know that an idea is wrong. It's good to know that, okay, fine, I will stop wasting my time on that and move on. No, it's actually great, because
No,
that science is progressing.
yeah, that's
We
true.
actually know something that we didn't know before.
And knowing that you're wrong means you spend less time on it now, so that does make sense. Yeah, that is.
Yeah. And you know something about nature that you didn't know before.
Question for the chat from Min on Discord. Would you say that you feel more or less clueless between now and your undergraduate and graduate years? I presume he's talking about like physics in general. Do you feel more?
I feel No, I feel much less clueless. I feel over the course of my career, I've become a much better physicist as I've evolved, and just had the chance to accumulate more and more knowledge and try my hand at various things. Uh, but I also know what I don't know, and I now know. So when I was your age, I did not know how much I didn't know, and now I know how much I don't know, and it is vast,
And that is
absolutely vast, uh, and it's frighteningly vast. And one human lifetime really seems insufficient. Yeah.
question now. It's a rather specific question, but it became relevant now that this is the season of grad acceptances and like research acceptances. Research acceptances. What do you suggest for students who did not get into grad school this year to do best to prepare to apply again?
I would try and do something. I mean, take a year. You're forced to take a year off, and try and do something that speaks to your skills, to practically apply your knowledge to something. If you can get into a research group or get an internship that involves some sort of research, even if it's in industry, I would do that, because then that speaks better to the skills that you're going to need as a PhD student. Um, I think that's what I would recommend most. I do think that another option is to try and do a master's in physics to just learn some of the graduate course material. But frankly, coursework is not the most pressing thing. It's really demonstrating that you have both the skills and the fortitude and the perseverance to overcome obstacles to be able to do research. I think those are the most important things. And by the way, those of you who didn't get into grad school are in very good company. I think this was a very, very bad year in terms of people getting in. And I think it's partly because of the pandemic, that there just weren't as many spots open as in previous years. So don't be too disheartened either. Um, the other thing I would say is that you might want to try getting a job in the quote unquote real world to convince yourself that grad school is really what you want to do. Because actually, I suspect in the long run, most of you honestly would rather do something else besides grad school. You may not realize it yet. There are a lot more things to do with a physics degree that you just may simply not know about. Um,
What other paths other than academia have you seen or taken? Have you seen other people take in your career? Like, what are some of the greatest, good, successful stories outside of going to grad school that you can point us to? Because it seems like in the department, everyone, especially on this Discord, everyone seems to talk about, grad school, grad school, grad school, as if that was the only and best and ideal option after undergraduate. But like,
oh, it isn't. No, in fact,
frankly,
in
yeah.
fact, I honestly think the grad school should be the exception, not the rule. That for the vast majority of you, it's you will enjoy going out and working in the quote unquote the real world, working at a company or something, doing. I mean, it again depends on whether you're experimentally or theoretically inclined. If you're theoretically inclined, you might want to pursue uh, opportunities in Silicon Valley or data science or something like that, or in finance. Uh, um, if you're experimentally inclined, I think there are lots of opportunities out in industry to do experimental research. And it may be research applied towards generating a product that can be sold, but you will find that as intellectually interesting as many PhD physics programs. And by the way, also a lot more lucrative. Um, and frankly, yeah, I mean, I'll just be blunt. Money is not a bad thing to have in your pocket.
Money is not a bad thing to have in your pocket. Um, Question about research from the Twitch chat, from Comrade Deco. Is unofficial unpaid research position okay? Since my group is a bit scattered and acts as both a reading group and a research group.
Unpaid research, okay in terms of preparing for grad school? Is that?
I would say, yeah, in terms of preparing for grad school, getting into grad school.
Yeah, whether you're paid or not is irrelevant. It's a question of whether you can actually demonstrate progress on a research problem. That's the key. And if you can do that, and you have someone who can say that in a letter of recommendation and speak to your skills, that is gold for a grad school application.
I think we have time for we have 10 minutes left. We have time for just a few more questions. Natalie asks if you can show us your adorable cats.
Do you want me to go get them?
I believe that is the case. I believe that is the request.
Okay, they may not be happy about this, but let me see if I can go grab one of them. This is one of them. This is Dobby, and you probably all know who Dobby is named after. Hey, Dobby, say hi. And if I was also to boast about our pets, we're both a bird and a cat family. So we have cats and we have parrots, and the parrots are also absolutely wonderful.
Oh.
Very intelligent, very, very unique personalities. What is it, Mr. Dobby? So that's Dobby.
That's Dobby. Precious, such a precious. A question from Jacob in the Discord. What do you do to unwind from physics?
Oh, I'm going to sound so during these pandemic times, you know, the options are limited. I mean, normally, if we weren't in a pandemic, what my husband and I really enjoy doing is going down into Los Angeles and going to symphony concerts, eating out at restaurants, going to plays, theater, all sorts of things like that. And we, you know, we have season tickets and
There's not much
stuff
to do
like
in Santa
that.
Barbara.
I'm sorry?
There's not much to do in Santa Barbara.
I don't live in Santa Barbara. I'll explain that in a second here. So my husband works at JPL in Pasadena.
Oh, okay.
He's an antenna engineer, and so we commute. He commutes south and I commute north. So we actually live in Thousand Oaks, which is halfway between Santa Barbara and LA.
You live in Thousand Oaks?
Yes.
Oh my God, I live in Tarzana.
Oh, okay. Yeah.
Yeah, we go in the same direction.
Yeah. No, yeah, that's right. That's right. So normally, you know, before the pandemic, there was an Amtrak train that I would take, that I would commute up to Santa Barbara every day, up to Galita every day.
Take?
I'm sorry?
How long would that Amtrak train take?
It takes about an hour and a half or so, but that's okay because you know, you're not behind the wheel.
That's true.
And I can work. I can do other things like read for pleasure. And by the way, that's actually what I'm doing these days. I've become obsessed with California history and culture, and so I read and read and read. I read a ton of things. Right now, I'm reading a book about the Chicano moratorium that took place in the early 70s in East LA, and yeah, it's wonderful stuff. Yeah.
Interesting. That's interesting. One more question, I think, going back to the topic of research. I want to split this question into two parts. What do you suggest to undergraduates who are trying to get their foot in the door in a research lab and in general? And then I want to add add an extra question is, what would you suggest for undergraduates specifically wanting to get into your research lab? Like, I don't know if
Yeah.
do you
So
have like do you foresee of having any openings in fall of 2021, maybe one position open, and how can everyone here fight for it? What's the best shot?
I mean, that's the problem, right?
Yeah.
I like most theorists. I mean, there might be, I can't think of any right now, but there might be theorists who can actually handle a larger number of students than I can. Um, I simply don't have enough projects that an undergraduates that they can do usefully, that they can actually take on. Uh, so, I have worked with undergraduates, but as the undergraduates who attend my group meetings will no doubt say, it can be a long time before we come together with a project that's actually suitable for them. Um, uh, in terms of getting into experimental labs, that is tough right now. But the only thing to do is just to continue to reach out to the professors, to the graduate students and the postdocs who work in those labs, and continue to just make contacts with them, get to know them, and try and see if there are any opportunities. And you just have to continue to pester them, and pester me for that matter, in order to make these opportunities happen. And that is particularly difficult during these god awful pandemic times. And I really feel for all of you. I will say this only happens once a century, so it's not likely to happen again in your lifetime.
Well, Dr. Blaze, I think this will conclude a very successful interview. Thank you for giving us an hour of your time. And this interview has been recorded, and we plan on putting it up on YouTube. But if you have any issues with that, like you don't want your responses out on the internet, just let us know now, and then we'll just refrain from putting your episode on YouTube. But like with your consent, we would like to upload it.
I have nothing to hide, so yeah, I think that's fine.
All right, then. So with that, I'm going to conclude the AMA with Professor Blaze. Thank you for coming, and thank you all for posting questions and asking questions. And I will see you all tomorrow with the interview with Professor Feigenson. Thank you very much.
Thanks
And
for having me.